So hi, we're getting started again for the second week. Once again, this is doing a quick review of the types of information and data structures and algorithms that you need to know to be prepared for applying to Google. You will need to keep kind of expanding on these, but these are the basics that everything's built upon. And unlike last week, I'm not going to have a little bit of the screen in there, so I'll just kind of talk through what slide we're on. Mostly because the slides are all online. What I'm drawing on the board is not, and so hopefully that'll show up better on the video this week than it did last week. And better markers today, and so we'll kind of jump right in. And so last week we talked about two kind of data structures that were kind of important, which were linked lists and arrays. We're just going to start by saying what are some of the differences between these things. Because the stuff we're going to talk about is actually kind of things that build on top of this already. So who can give me some difference between one of these groups and the other? What's something, how would you describe a linked list? Walk me through it in any level of detail you want.
It has a thing and then it points to the next thing.
All right, it has a thing and it points to the next thing. That is perfectly accurate. So we're going to make it some boxes representing our items in our list. We can kind of go on for some amount of time. You keep some data with the element, and then you keep a pointer to the next item on the list. How does an array work?
Chunk of stuff in order.
Chunk of stuff is a very good explanation for how an array works. Because you literally set aside a big continuous block of memory. It's kind of divided into pieces. And you know that the second item, these could be one index if you prefer, but you can figure out where the second item is because each one is the same size. And so because they're all the same size, you can jump from one to the other. So these are kind of two of the pretty much lowest level data structures you can get, and a lot of things kind of build on top of them and kind of make assumptions about how these things are arranged and what data is stored in each one. And that's really a lot of kind of how data structures got more complicated. It's because they started making assumptions and putting rules in place for what it means to go from one point to another. And so we'll start by talking about a stack, which is, in some sense it's a data structure. In another sense it's just kind of an abstract term that people think about. And it's not really something that is per se computationally powerful. It just lets you think about things easily, so when you say stack, people know what you're talking about, and they know some basic properties about how it should work. And so if you were to take the real world item called a stack, if you were stacking blocks, what were some things that might be properties of a stack of blocks? You have the ground.
If you try to take the one not at the top, it falls over.
That is exactly the key property of a stack. So you put things in, you put the first item down, put the second item down, put the third item down. If you're playing Jenga or anything else, and you try and take the one from the very bottom, you screw everything up. And so you can't do that. And so a stack, you only can take the top part. You can only place items onto the top, and you can only remove items from the top. And so it's another name for a stack is a last in, first out structure. And so as it's described, whatever you put in last is the first thing you pull out. And it's pretty simple, it's pretty basic. And everybody smile and nod and say this is a reasonable thing that you can understand. Does anybody know why this is a really important thing? I don't know if you guys have cheated, but these are really important things. And so it's really important because it comes up in computers for how they actually deal with the commands you give them. Because in computers, you have something called the calling stack. So when you call a function with some parameters, what it does is it says, I'm living in the global space, and then I'm going to store whatever my global space is, put a new set of stuff on the call stack, and say, aha, I'm I'm in this function space. And then you can kind of work with that for a while. And then when you're done, you say, I'm done in this function. I come back to the real world or the working space that was above, and you can suddenly get back to all the variables you were before. But you could also kind of nest that further and say, F1 calls something, and then maybe F1 calls some other function, F2. And maybe that calls something F3. And so you can kind of build this stack of things where when you finish with some function, unless you do some particularly nasty programming things, the only place you ever go is back to the function you just came from. And so this is kind of an idea that'll come up a lot, because you can change this from being F1 calls F2 to F1 calls itself. And if you set up the function right, you can use a lot of powerful properties with it. And anytime that and these are called recursive functions. Right now I'm just going to write recursive on the board, and that's about all we'll talk about this week. A lot of the algorithms we're going to talk that deal with these data structures can be written very nicely in a recursive form, and are really easy ways to think about problems. But it's important to realize that anything you do that's a recursive function is just building a stack of calls. And so it's storing variables in this stack. And so this stack is actually how your computer represents things, and there will be kind of always trade-offs between the two, or equivalences between the two. So anything you can write a recursive function to do, you could also just use a stack data structure to do the same thing. And we'll see some examples of that, and we'll actually walk through that process in next week. But for now, we've defined a data structure. That's a stack. Does anybody have any questions on this? I'm going to have some questions and thoughts for you to ask.
Is that just like a theoretical implementation, or is it like a physical?
This one for the call stack?
Yeah, for how?
Yeah, computers actually have literally a call stack. It has some more constraints about it in terms of how it's exactly set up, but there literally is a call stack in your computer. And when that runs out of memory, that's one of the things that can make it so that your recursive function has gone too deep that your program crashes.
Okay. So it's in like the main memory, which is where this stack is?
Yes, in some memory that the computer uses for, I think it's set aside in a somewhat special place so that your program can't mess with it too much. But yeah. And so, kind of based on some simple properties of how a stack works, would you implement a stack using a linked list or an array? Any thoughts, any ideas? Do you have a stack? Pardon?
Linked list?
Linked list. Why?
More dependent.
What's your question? You're raising your hand.
Yeah, well, I was just thinking, the structure of the linked list, it seems pretty similar to a stack in the sense that each item has a direct relationship to one particular item, insofar as like the next one.
Yeah.
There's a particular one that comes next in order. So it seems like you would have to build that into the array, whereas it's already built into the linked list and kind of implicitly with the address.
That's a great answer. And so yeah, so from kind of a conceptual standpoint, having something like a linked list where you know kind of the address where one goes into the next, is a really handy way to do it. And so that is the right answer for this class. I can't quite recall because it's been a while since I did this part. I think they actually use something closer to arrays because they do it at a very low level in assembly with how these things are actually written. So they use something that's kind of a hybrid between the two because it's not quite a regular array either. But this is generally speaking kind of how stacks are used to get the call stack. But the idea is still the same, and it is very related to a linked list because you can only get from variable that you have, you can only get to one other variable, which is the one underneath it on the stack. So, in your free time, I encourage you to try implementing it both ways. Any other questions on it? Awesome. So now we're going to switch over to talking about, to give a little bit more preface today. We're going to talk about a number of different data structures and then how they relate to kind of these two simplest cases. Some of them will be more similar to linked lists, some will be more similar to arrays. And they all have different uses and different reasons for why you think about them the way you do. And stacks, although very minor, will come up again next week when we talk about more about recursion. So now we're going to switch into hash maps or hash tables. And these things are called by different names in different programming languages, but they're really useful. But it's also good to know their limitations. And so, hash maps are the kind of magic behind dictionaries in Python, but they're also, generally speaking, very similar to how structs work in MATLAB. And so they can be used for kind of similar things, which is you can put something that we call a key, which is just some piece of data. Often we use strings, and so you can use the name of something, and you connect it to some value. So these are often called key value pairs or key item pairs. And the nice thing is they can have essentially any or no relationship other than the fact you put them together. So it's really nice. They don't have to be in order. You can have the keys be kind of anything you want. Structs are more limited, but they have to be strings, but you could have the key X in here, you could have the key be the numeral 1, you could have the key be the value none, even, I think. So you can do lots of things with the different keys. And it's a question of how do you map a key into a value? Does anybody have any ideas on how you might turn a key into a value? Like, how do you go back and say, well, you know, I have this key, I want to uniquely identify it in some way? Let's see if I can answer that. Okay. This is very, not the best question. So we're going to keep working on it. So, given a linked list, if I told you that there was some magical function that always produced the same value every time you gave it a key, which we'll call a hash function. This thing actually exists. This function called hash. Every time it produces a value, or every time you give it a key, it produces a value. And that value is guaranteed to be returned the same way every time. What could you do with that with a linked list? This is kind of a trick question. The answer is not much. It wouldn't allow you to go anywhere. But if every time...
Can you use like the key as the edge or the pointer and the value is the next thing in the... I don't know if that's...
So the key goes down here and the value goes up here?
No, the next one. Yeah. It's like pointing to the...
Like the key is the address.
Yes, that's kind of what we're going to get close to.
Well, I think as long as your keys are unique, then each item in a linked list could have two pieces of data, a key and a value, and your program just walks through each item and says, is this the right key? Yes, okay, take the value. If not, go to the next one.
Yep.
And it wouldn't be terribly efficient, but it would work every time as long as the keys are unique.
Yeah, that's correct. You could kind of store both pieces of data in here, walk all the way through it, and what would the kind of big O notation order of that be?
10 over 2.
Yeah, so it'd be order n. And so take the full size. Hash maps are cool because they allow you to answer the same question with constant time operations. And we'll talk about exactly how good that is or when it's not good. So what do you do for an array? If you had a value called hash function that turned a key into a number every time, how could that be useful in an array? Let's give some examples. Key x, hash x equals 1, hash of 1 hash of none, 0.
And where does the hash notation come from? Is that within Python or?
This is within many, many, many programming languages. So the name for a function that you give some piece of data, and that value returns, or that function returns a value that is guaranteed to be constant for that data, is called a hash function. So it's just kind of a term at this point. But so now that we have these values, or these hash values, for different inputs, how could those be used with an array? How might that be? So what happens if we start storing pieces of data in these indices? So we could say, well, every time you pass me none, I convert that number to a 0. I think this is the idea you kind of suggested. And I just go and store whatever data was supposed to go with this none. So we can go and store Z in here.
Doesn't that constrain your value to be the same size throughout the array?
Say that again?
Doesn't that constrain what you put as a value?
Fair enough. Good point. So we'd make a reference to Z. So we have a reference to Z. That's a good point. Depending upon what you're storing, you might be able to get away with doing the raw ones, but a reference is more typically done. That's a good point. And so then in position 1, so the hash value of x turns into 1. So we can store the data that would be associated with that key.
Wait, I don't understand how you're linking it. You're like linking up multiple things here with like the hash value creating always numbers and then the...
Yep, that's exactly the correct summary. So a hash value takes any piece of anything you give it and returns a number. And so that number then can get turned into an index in an array. And so like a simple way of doing
How
it,
would one set up this hash? I mean, because it doesn't just return it randomly, and you need to make sure it doesn't create overlapping numbers.
yeah, and so that is beyond my expertise. There are lots of ways of doing hash values. There is a whole lot of science that's gone into kind of designing good algorithms to produce hash values. Because some of the problems we were talking that you just mentioned was that if you always have a hash value that returns 1 for every single input, it's a valid hash value. It gives you an input every time you give it a number. It's consistent. But it doesn't have a nice property of being uniform. You want something that will uniformly cover the entire space of possible values. Because then it makes it unlikely that two of these things will collide and end up in the same bin.
Well, to do that, you need to know the size of your array. Or how many.
Yeah. Well, so you can always do kind of a quick trick, which is just to take whatever value gets spit out and do a modulus operation, just to take whatever amount of it would fit inside the array. And so, yeah, I admittedly do not know the best hash function to use. There's all kinds of cryptographic ones you can use if you want something that's really going to be kind of uniform, but then it ends up being, it takes a long time to compute, which is part of why they're cryptographic ones. There are much quicker ones that you can do that just do some bitwise operations that tend to produce a pretty uniform distribution. So when you take something that's relatively uniform, use a modulus, it still stays uniform. And so you get things that generally don't fall in the same bucket.
How do you know what kind of inputs? So a hash function is like it's a constant thing that exists, not a thing that I write, or?
Yeah, I'm just confused as to how this would be applied. Like what this means, like you give you pass all of the data that you want to be converted into these numbers into something at the same time, and then something happens, or like what?
Yeah. So normally, all you do is you call a function that creates a hash table. And it does this, at this point you just use library functions to do it for the most part. And what it'll do is in the background it'll create some array that'll hold the data. And then it has rules for how you go and Where did it go? Then it has rules for how it gets filled. And so you can supply your own hash function if you want, but typically these are built into most programming languages. A simple kind of example of one is if you took every bit and stepped, or if you took every couple of bits and stepped through it over and over again and applied the XOR function of one set of bits to the next set of bits to the next set of bits.
What is XOR?
So XOR is if you have, it's an operation that if you have 1 and 1, it'll give you a 0. If you have 0 and 0, it'll give you a 0. If you have 1 and 0, or 0 and 1, it'll give you a 1. So it's just kind of a logical operation you can do on bits. And if you step through a bunch of different values, and you do this, and then you take whatever came out of the end of it, and pretend it was a number, that number will often be uniformly distributed. And so this would be an example of a hash value. I don't think it's one that people actually use, but I could be wrong.
So, if your program's going to use multiple dictionaries, you're going to have multiple arrays so that they can handle keys differently, right?
Correct.
So, it seems terribly inefficient if it's going to create a whole crap load of zeros for your values every time you create an array, right? Like, are these arrays just naively, they seem like they would have to be gigantic in order to store any, otherwise like the potential like key, would be really limited so that you could create an array that's relatively small, or am I just simplifying it?
So I think what you're referring to is the fact that unless the array is really big, keys will probably collide.
Right.
Or you'll kind of run out of space. And so there's, this is another reason why these are usually implemented in a library somewhere, and you need to know how to use them, but you'll probably never write one yourself. It's because people spend a lot of time figuring out how to make it so that these things will grow automatically. Like once you start adding like 10 keys, maybe it'll double in size. Once you get up to 20 keys, it'll say, well, now I'm starting to get a little dense, I better double again. And so they have things in there to say, how does this, when should I increase the size of the array that I'm using? And it has things in here saying, what happens if I happen to give you 2 keys that have the same address, or that have the same hash value? Particularly for kind of a small array, that could happen. And so kind of one implementation and one simple way around it is that at this position, rather than storing directly a reference to y, store a linked list. So then everything that comes here does exactly that method you talked about of stores the key and it stores the value. But if you have like 300 things, you kind of reduce the length of that list by 4 now. Okay, 300 out of each one of these. You wouldn't have to search through all 1,200. You'd be able to search through a much smaller set. The real implementations people use are much more advanced than that. But because they get much more advanced and I don't even know them, I'm not going to go through the exact details. But it's more the idea that anytime you have any input, you can convert this input into something else. In this case, an integer. And you can use that integer as an index into an array. And this is something that allows you to map values of any type into indices into an array, which you can then use to retrieve arbitrary values. And so there's a little bit convoluted way of getting there. I see some head scratching.
How is this different than just assigning the reference of a Spider array?
So what if you want to store, what if you don't know what these things are going to be, or how many you're going to have? How would you design that to work?
If you create an array, it has a specific memory address for each index, right? So you could still link the memory address to the key, and then if you change the value, it's going to come to it.
And so what if you did this and you said, I'm going to use all of the values in the first half of the alphabet. These are all going to be the key values that I'm going to use. You can map each one of these to a point in the array. What happens when somebody says later, that was great for your problem. I want to start using the entire alphabet. How would that fit in that mapping that you made?
You'd have to add to it.
You'd have to add to it. And so hash maps make it so that you can build a data structure that you never have to add to yourself. Everything gets done by the computer where no matter what set of values you give it, like you can start giving it numbers.
Wait, value, you mean keys?
Keys, yes. My apologies, I should be more careful. So, thank you. So you can give it any type of key you want, and you never need to change what your hash map is using. It has an algorithm that will handle any type of input. And so even though for your problem you started off defining it as the first half of the alphabet, somebody came by later and used it for a different purpose, that they could still use that same piece of code, and any optimization you did on your piece of code will also apply to their piece of code. And so it's kind of a way to get a lot of reuse out of code. And so it's kind of an example of a data structure that you can get a lot of power out of, and you can get kind of fancy things out of, that you might be able to get kind of a simpler kind of data structure as a one-off case, if you wrote it yourself as a one-off case. But there's a lot of power in the ability for these to kind of scale to all kinds of problems. And if you don't know what kind of data is going to be coming in, you can't write a custom-made data structure. You have to make something that handles arbitrary input. And that's often a kind of a problem that comes up. And you can use these in kind of as a nice trick. For example, these dictionaries are actually how all function calls are handled in Python. Every object just holds a set of dictionary, or a dictionary for all of the things it has in it. And if you pull something out of the dictionary that's a function, you can use it for a function call.
If you make a number a key, if that number is just a random number, does it replace the data with, like if you're assigning a new variable and that number, but you want it to be that number, does it just go and follow like the key?
Yeah, so that depends on the hash map,
Okay.
or the hashing function. And so that's a good point. Like, you could think of any array as a hash map with a key that's an identity function. It just returns the same value as the index, as whatever key you used. And so that's totally a valid interpretation of it. And these hash maps are just a way to generalize that kind of ability of an array to say, give me element 2 to any type of variable. Now you can give it strings, you can give it objects in some cases. You can give it all kinds of things you can then use to switch back and forth and say, okay, if I have the complete works of Shakespeare versus the complete works of Yeats or something, you could use those as keys, despite the fact you would never have thought of that beforehand. But you can do it. And the kind of key benefit for doing that is how long does it take, what's the kind of order notation for finding a value if you have a key? How long does that take to do in big O notation? It takes a constant amount of time. All you have to do is you compute a hash function, or you take some modulus or something to map into some location or make sure it fits, and then you know exactly where it is. And that's pretty cool, because that means that you can take any data and you can get to it in a constant amount of time. The issue though is constant depends on the hash function. So for example, if we talked about something that returns a unique key and is guaranteed to be constant for any given input, and like completely reflects that piece of input, if you had the complete works of Shakespeare, guess how long it would take to go through and compute a unique key? You'd have to look at every single letter and every single value in the complete works of Shakespeare. And so hash maps are constant in terms of the number of items. They're constant time operations to get to an item. But that constant time can depend on the hashing function. And so it's order 1 for the number of items you have, but it's order constant in terms of whatever your hashing function is. And so for doing something like the complete works of Shakespeare's keys, or something else that's like a really big data structure that's really hard to compute a hashing function for, hash maps don't work that great. And so sometimes, even though this is like order 1 to find an item, If it takes a long time to compute the hashing function, it might be faster just to go through a linked list. This is just kind of a case where like they're great for a lot of things, but in the wrong cases, they can really slow you down more than you might have thought. So did that point make sense to you? Question?
Can you, like, would it ever make sense to kind of do a hybrid where you have like another dictionary stored as a value? It's kind of like what you were saying with the linked list instead of a reference to a linked list instead of a reference to the value itself up there. Is that ever implemented except for explicitly? You know, like, I'm trying to think about what normally happens when I like define a dictionary.
I don't think, I mean, admittedly, when we get to like the nitty-gritty details, because they have a lot of complexities of how do you make sure that they're always big enough to hold your stuff, what happens when there's collisions, there's a lot of different implementations, so I can't give you a 100% for sure answer. I don't think there's any reason to do it, generally speaking, unless you kind of program it to happen. You can, of course, program a dictionary to be inside of a dictionary, or a dictionary inside of an object produces that same effect. But anytime you're kind of mapping a thing to a uniform space and another uniform space you want to map it over, you could. Yeah, maybe it's a good way to go. Admittedly, I'm not sure. Maybe it does that under the hood. You could, because then you get the same type of effect. Like, let's say this is only going to be 5 elements long. You could do one of these that's 5 elements long and just nest that some depth deep. And if that keeps kind of going infinitely deep, you get the same hash value all the way through. So that would not work, actually. The different lengths. I'm not sure. It could be potentially useful, depending upon your problem. And so all these things are always only useful for the problem that you're actually trying to solve. But, yeah. Unfortunately for this one, I can't walk you through a very terribly detailed implementation because there's just too many different ways to do it. But the key points are that you can get constant time access for arbitrary keys, which is helpful for them. But that constant time can take a bit of time depending on what that key value is. So we'll move on, and we'll start talking about yeah, and that's mostly kind of what we'll talk about for arrays for today, and things that base off of them. And now we're going to talk about kind of generalizations of linked lists. Specifically, what happens when you no longer point to just one value after you, but you point to 2 or more. And so, kind of the standard example, since we're all mostly biologists in here, is you can think of like a phylogenetic tree or something, or any sort of tree. We have one kind of root of the tree. In computer science, they're often drawing coming down, going up for biology. And it splits off, and it has, in this case, 2 children is most common. This is a binary tree. It's all the left child and the right child. The node up here is called a parent. And they're pretty easy to think about, and they're really common in terms of programming questions. If you get an interview, it is very likely that somewhere in there, there will be a case of a tree, and that tree will probably be binary. Just because they're really easy to think about, talk about, and use algorithms for. And anything you can do on a simple tree, like a binary tree, can probably generalize to something more complex. And so we'll talk about, many of the algorithms we'll talk about next week will take place on a binary tree. And yeah. And so so based on some of the things we know about linked lists, what are some things that might be good or bad about a binary tree? Like for example, how long does it take to put an item in a binary tree? Yeah, how long does it take to add a new node? Keeping the restriction that it has to be binary.
It'd be less, right? You put more data with less movement.
Yeah, and so let's walk through that in particular. And so this will be the average case. So we'll talk about a little bit more how it happens. But can you explain that a little bit more? how could it be less? How could you end up needing fewer data accesses to get to a point?
If you wanted to like store 6 pieces of information, if it was just a standard linked list, you need, I don't know, 6 times 5 times 4, right? To put each one in, each one would take one more movement time.
So being able to like put something on the end.
Right.
Okay.
If you have a binary tree, you can add 2 without moving more than 1 step, and then add 3 more without moving more than 2 steps.
Yeah. And so if you kind of keep all the things you're holding in context, like maybe it takes a really long time to get up to memory and get these things from disk or something, that kind of cost, or if you have to do it over a network, that cost of getting a new node can be really expensive. And if you have to pay that for looking at every item, that can be really slow. But if you can get like the next 5 addresses all at once, you can kind of do them asynchronously and just be waiting for the network to give them all to you. And so that's one way that you can spend less time because you can do more of it in parallel. And so yeah, that can totally work. And the reason for that is because it does this branching out. So it allows you to kind of manipulate everything kind of side by side. So like let's, so what would be, let's say that we have a bunch of these lists that were, or these trees that were randomly generated, kind of from all possible combinations of binary trees. Does anybody want to take a guess on like what is the worst possible amount of time it would take to add something to the end of the list? Like if you were just going to like take random guesses between going to the left fork and the right fork, like what is the worst possible value in order and notation that it would take to get from the top of the tree to the bottom of the tree, where you could add an item?
Do you have to start over from the beginning?
Yeah, well, so you start here at the root. So this is often called the root, it's the top of the tree. All you're doing is you're looking for a spot that has an opening.
So it'd be choosing the one that has like the maximal number of children, essentially, right? Would be the one that would take the longest to get to, if you were just randomly choosing each time you jump down. Because like, no? I don't know.
Let's say,
I mean,
maybe we have to put on.
I don't know. So I mean like, because like in this case, for example, if you chose to go to the right, it'd be faster. But, or you could choose to go to the left, but you have to jump further down because it has like more children associated with that node or something.
Yeah, and so the question is, can we figure out what the absolute worst case is for the minimum, or for the minimum number of steps you'd have to take before you find some opening, such as over here or over here?
Almost squared, right? So you'd have to go through every one twice to go down and then back up and then down and then back up.
So you can store them in as some data structure, things you visit, and you actually never need to do that. And so what happens, so like we're going to keep working through this example.
Is it just the number of arrows?
It's actually a small number. It's smaller than all the guesses I've heard so far. Because all you're trying to do is you're trying to start from the bottom, and you're trying to find any space anywhere. So what happens if we like just went all the way down the list, all the way down to this longest distance? About how many did that take? 2 steps, and we found something. If we went down this side, how long did it take?
1.
That took 1. And so this number is less, and so therefore it can't be the worst case. So something like this is going to be our worst case. We can draw a couple of other examples and think about how these examples would work, and then see if that can help us answer this question. This is a relatively balanced tree. And so by balanced, it means it has about the same number of stuff on the left as it does on the right. So if we drew another circle down here, now this is a perfectly balanced tree. And anywhere we go, we have to take 2 steps. Instead, we can go like the complete opposite for a really unbalanced tree. So does anybody have an idea of what an alternative name for a completely unbalanced tree is? A linked list. So if you have a linked list, it's actually just another way of thinking of an unbalanced tree. And so anything you could do to a tree, you could eventually do to a linked list. If you change how you associate with it. How long would this take to find an open spot? There we go.
Constant time.
So 0. You could add something right away. So generally it's always best to think about like the extreme cases anytime these questions come up, and if they come up in an interview and somebody's like, oh, how long would it take to do this? And if you're not sure, like how long would that take? You can do it right away. And the other is to think where everything is perfectly balanced. And so even though you have 7 items in here, it took only 2 steps to get there, to get to some place where you can add an item. And so, could anybody take a guess on what the name is for the kind of big O notation cost? Yeah, it's decreasing in cost based on the number of items in the deck. It's the logarithmic growth. So as you add kind of more things, these spread out more and more, because you can fit more at each level. And so that means the cost to kind of find the end of it is logarithmic in terms of the number of items. And so for a binary tree, it's log 2. So that's how much you kind of separate out. You grow, you double in size at each step. And so kind of the worst case for this is a log n. And so, if you're just looking for a spot to find, you can do it log n. We already talked about it. What would be the best case for how long it would take to find something? Yeah. It'd be constant time. You'd be able to start there right from the beginning. And so once again, we talked about these being kind of opposites of a tree, a completely unbalanced tree, or a linked list, versus a completely balanced tree, where it's order log n. And so we'll take the next step now in the slides. I believe we go from a binary tree to a binary search tree. And now we have to start introducing numbers, because you don't do this, you don't do a search over, binary search trees are only useful in the sense where things are ordered. And so typically the way you do it is you assign numbers to things, and we'll start by assigning value 5 to our root. And the definition of a binary search tree is that everything that is in the left child and to the left of this root node must be less than 5. And so we could assign this one the value 3, this could be 4, this could be 2 and 1. This perfectly specifies, it's the only way you can structure it. This would have to be 7, 6, and 8. And so, yeah. This is generally kind of how a binary search tree works. And if you were to switch these 2 values down here, would you have a binary search tree? No, you wouldn't, because you'd go from 7, and then 8 would be on its left side. It's not very useful if you could do that. And so with binary search trees, they are handy because let's say you want to find an exact value. This is something we'll do now. This is actually one we'll cover a little bit more next week, talk about some variations. But what if we wanted to find the value 2? We'd start at position 5, and would you know where to go from here? Where do we go?
Left.
You go left. We start from position 3. Where do we go from here? You go left. Aha, we found it. So if you're trying to find something, can somebody guess what the kind of cost would be, the order n, order whatever, for finding an item in a binary search tree? Log n, because? Yep, because you know always which side you're stepping on, and the number of items that kind of are at any layer grows, well, in this case, exponentially, which means that you cross off kind of an exponential number every time, and the cost is logarithmic.
How do you know which side to go?
Because the definition of the tree is that everything to the left is less than this value.
Oh, okay.
And so it's just part of the definition. And so there's examples in the code online of how you would actually create a binary search tree. And it has rules that when you say like, aha, I want to add a value here, how would you add the value, let's say 9? What would we have to do to add the value 9 to this tree? So we're starting here, at the start, at the root.
Go to the right choice.
Yep. And so we say, aha, can we add the value here? No, because there's no open children, especially not one to the right. And so we say, aha, we have to go over to 7. And then we can say, well, can we add any children here? No, specifically not one that's greater than 7. So we come down to 8, and we can say, aha, can we add any children here? Yes, we can add children. Do we add it to the left? No. Do we add it to the right? Yes. So we create a new node at 9. And so this could keep going if you keep adding things sequentially to a binary search tree. For example, let's say we add the number 10. Come back down here, say, well, we have to add it to the right child. And it goes down the list. And so what happens if you start a binary search tree with nothing, let's say the value 0 at the root, or whatever the first value is, and what happens if we add the numbers 1 to 100 in order? Yep, we get a linked list of values all the way up to 100. And so you can, if you kind of take a quick naive way of making a binary search tree, you can get a linked list, depending upon the order that things are added in.
But, so, can you only have a number once?
So yeah, oftentimes you make a definition of what happens if you get a doubled number.
Yeah. Because like, if you were just following that basic rule, you could add the number 5 in 2 places right now, right? Because you could be going up from 4, 3, 4, 5, like by going to the right.
Yeah.
You could be going down from 6 by going to the left.
Yeah, actually with the rule I said, there was nothing about what happens with doubles, and so you would never be able to add it. But that's exactly the question that somebody has to answer at some point. And generally you just pick one. So you just say, rather than this being everything less, this will be everything less than or equal to. And so you just have to define which side the equal to happens on. To go through this example of adding the 5 down here,
Yeah.
that would say that everything on the left is less than or equal to this value. Because then you'd have a 5 here. And that would still allow everything on the left side of this to be less than or equal to. But if you made it, everything has to be strictly less than, so everything on the right is greater than or equal to, then, well, it's equal to here, so it must go on the right side. And then, well, it's less than this, and it's less than here, so you'd have to add it down here. So you're right. You could end up in pretty much the same spot, and it's just a question of which kind of parent are you connected to at that point. And all it is determined by is what choice you made for that rule. I don't think there's I'm not aware of any reason why you pick one over the other. It's kind of whatever that particular programmer was feeling. But that's an excellent example that a lot of choices are arbitrary, and you just have to pick a value, and it still makes the whole thing work. And so we talked about this example of that this problem could happen. We won't go through how it works, but can people think of how you might avoid this? What could you do to prevent this list or this tree from turning into a linked list? Or in an abstract sense.
The top should be the most parented one, whatever it should be 50.
You mean just if you want to have, if you want to have all of these values somewhere in something?
Yes, so if you wanted to try and convert this tree, this linked list version of a tree, this heavily unbalanced tree, into a balanced tree.
So what Ken said.
So I would say the top would be 50, and then you would stick in like 75 or 25 next, and then just keep splitting it until,
Or just have it be random instead of pre-sorted.
yeah.
Isn't it with like sorted algorithms, they always do the worst on pre-sorted lists?
But if you
Some
do
people
it
do,
randomly,
but,
it's not going to be balanced though, right?
On average, it will be balanced, if you can actually randomize it. But the problem is, if anybody can figure out your randomization algorithm, they can screw you over every time.
On average, it'll be
Which people
balanced,
like-
but in practice, none of the particular examples will ever individually be balanced. Unless you happen to get extremely lucky.
Most likely.
Right.
Yeah, and so the way people have done that is because it has this problem that like, yeah, you could randomize everything, but what if you're getting these in turn and somebody's just giving you a number and you have no idea what's coming next? You can't really randomize it. And you have to take everything in turn because nothing else exists yet. So you need some way to deal with it kind of as it's coming in online. And so the trick that people have come up with is that you could take some part of the tree and you could do exactly that thing where you take it and pull it up to the top. And you just pretend, aha, this is the root of the tree because it's in the middle. I'm just going to string everything up from here and kind of reorganize the leaves so they fall into place. And we'll do kind of an example for one of them. So for example, what it takes to make, this is called a rotation, if you ever need to know the term. We're going to rotate this 7 up to the root of the tree. And so what do we have to do to make this 7 top of the tree?
You rotate it.
Good answer. Can you give me, so I think there's 3 steps in rotating it. What would be one of the steps you have to do? And what's the end condition we're trying to get to? Perfect. One of the things that's going to happen sooner or later is we're going to have to get rid of this pointer from 5 to 7. What else do we have to do?
Reconnect the 2 parts of the tree.
Yeah. In which direction?
So you know that 6 is greater than 5, so you can just like plop, create a new line from 6 to 5.
Yeah. That is actually a good way to do. In this case that we have perfect information where we know what the whole tree looks like and we can do it. There's a way you can do it every time, even if you have no idea what all these values are. For example, it could be that 6 has 2 children. How do you say 5 and 6? So maybe we can't predict what all the children are off of here. There's still a way, it takes, in this case, 2 extra steps. There's still a way we can do this rotation, only using this node, and this node. And so you're close to it, which is we need something that points to 5. What could end up pointing to 5 out of these 3 nodes if it's not this one? 7. We make 7 point to here, but now this guy has 3 connections. And so what are we going to do about that? Because obviously that can't work in a binary tree. So we need to get rid of one of these guys' connections, but we don't want to lose it entirely. So we,
And 5 only has 1 child.
let's say that again.
5 only has 1 child.
Exactly. 5 only has 1 child, and 6 is bigger than 5. So we say, let's draw this arrow down here and steal it from 7. And so now the root is right here. I'm lazy, so I'm not redrawing the whole thing. But you can start here, and now we still have this binary tree, this binary search tree property, where everything on the left of this 7 is less than or equal to 7, and everything on the right is greater than 7. And so there's rules that you can do this online, so that every time a value gets added to a tree, you can do the proper rotations so the tree stays balanced. Generally people use the term approximately balanced, where it's within 2 log n, but it's fine.
Right?
Yeah.
Why don't these have to be directional? If you had them all reciprocal, you don't have to redraw anything, right? You just have to just pick a new root node.
Yes, the problem is it gets harder to do searches. You also need to store twice as many pointers when you do it. Yeah, we're getting to those data structures. In part it's kind of, you want things that are easy to think about and that solve problems in easier ways. The other thing is, how do you pick where to set which value to choose as the root if you're moving the root? And so, yeah, admittedly, I can't think off the top of my head kind of variations on it. I've never tried them with arrows pointing in both directions. It should work. there are some kind of other theoretical, or some other actual reasons for why trees are useful structures, in terms of how they group things together, and things move kind of as chunks then. Because we've talked about this instance here where it's like, at every point there's one value at every node. Sorry, quick digression. Red and black trees are probably one of the simpler examples of a self-balancing tree that keeps itself in order. They're cool to look up, and if you ever want to like find out a lot about how trees work, try implementing one. You usually won't have time to do it on an interview, but they're cool to look at nonetheless. Another type of tree that's also a self-balancing tree is called a B tree, where instead of storing one value at a position, you store a lot of values. So this is actually one thing that databases do. They store like a bunch of values. Each one takes up an entire block of hard drive space. And when you get that block of hard drive space, it tells you where everything is underneath that. And so you take kind of the biggest chunk that you can fit on a hard drive block at a time. And so there's some other kind of theoretical reasons for why, or some other reasons why trees are nice. Because it minimizes the number of queries you have to do to the hard drive. But you don't need to know that for an interview. And I think actually the next thing we're going to talk about is exactly the case we're thinking of though, which is graphs. So here we're talking a tree is an example of a graph. But generally, anytime you have nodes that are connected to other things, it's called a graph. And so a linked list is a type of graph that has just particular assumptions about it. A tree is an example of a linked list that has particular assumptions about it. And a graph is one that has, in some cases, particular assumptions about it. And so this one, I've drawn arrows on it. Does anybody know what this type of a graph would be? Pardon?
It's directed.
Yeah, it's a directed graph. So
It's not basic.
it is
It
actually
is
cyclic.
cyclic. It's
Yeah.
not cyclic.
And so this is an example of a directed acyclic graph, where,
Does acyclic mean it never comes back to a point?
yeah. So this is an example of a cyclic graph, but still directed. You can also do these without any arrows between them, in which case it is a undirected graph, which in this case still happens. Undirected graphs are almost always cyclic, I think. Could be wrong.
If that's more than one point, then it would have to be
Yeah.
potentially cyclic.
Yeah, I can never remember if the intrinsic or the connection back and forth counts in it. Nobody talks, I don't remember anybody ever talking about an undirected graph and whether it's cyclic or not. Yeah, and so these are things that are like super general, so we're not going to talk about it. Well, we will talk about it a little bit. Too much more than this, but we'll go back to our case, we'll go back to a simpler case, where we have 4 nodes. It's connected with this. Everybody see that? You have one connection, 2 and 3, and then both 2 and 3 connect to 4. How would you store this in memory? Or how would you write down this description of your graph? There's 3 different ways to describe it. Some we use more commonly in neuroscience than others.
One is an array.
Not an array, which is, oh, well, yes, but what, also,
So you could either describe it as basically 2 lists, an array, or I don't know what the third one is.
we'll get there in a second. Yeah, and so the array is often called a connectivity matrix, same as in neuroscience, where we'll have 4 different things, and there's just kind of a dot if they're connected to each other. So we can have 1 connects to 2, so this will be row 1, position 2, connects, 2 connects to 4, and so row 2 connects to 4. Row 1 connects to row 3. Row 3 connects to row 4. And we're done. How much space does this take up? If you're storing it as kind of a dense array. Yeah, so it takes up n squared. So for the number of nodes, it takes up twice as many positions. At the same time, it's really easy to read out. And so particularly if you have like a really dense graph where everything's connected to something else, or if these values have weights, so this is like 0.5, this is 0.6, which comes up in some problems. I won't really talk about it, but it can. This can be a nice data structure to work with, but it's really expensive because it's big. One of the other ones that Francisco was talking about is just a list saying what are the connections. So we have a list, we have a connection from 1 to 2, connection from 1 to 3, connection from 2 to 4, and a connection from 2 to 3. And the other
Wait, how is
is,
that
pardon?
is each of those a list? Or?
Each of these is just 2 points.
Still matrix.
Yes, it is still, so it's often called an adjacency list, so I'm sorry.
So this is using the word list outside of the context of like a linked list.
Correct. List is kind of a more general word, and linked list is a specific type of list. And yeah, there's lots of terminology, apologize for that. What do I call it? Do I call it association list?
Adjacency.
Adjacency, there we go. And so what is the size of the adjacency list?
2n.
2n, what is n in this case?
Number of nodes.
Sorry, incorrect.
Connections.
Yeah, it's 2n for the number of connections. So often these are called vertices and edges, and so it's twice the number of edges. Actually, no, take that back. Sorry, it's not the edges. No, twice. It's just exactly the number of edges. Because every one has space. Yeah. And so there's one more, which is
You can just kind of treat it like a linked list, like we were before with the binary tree. So, I mean, it seems pretty generalizable that any item could have any number of addresses that you want, and
perfect.
you can just, it seems like that could just generate any arbitrary graph.
Yep. And so we have our nodes, 1, 2, 3, 4. Each one of these holds either an array or a linked list of its connections. And so, I never remember what the term for this one is. It's one listed on here, it's a list of neighbors. Can't remember the term now. Yeah, so you have 3 different ways that you can store exactly the same information. This is something that'll kind of come up a lot at the kind of website that I point people to for example problems, Topcoder. Anytime that they have connectivity matrices, sometimes they give you this one, sometimes they give you this one, and sometimes they give you this one. And you need to switch between them to get the proper form for the proper problem. And so knowing that these are all kind of connected things, they're equivalent things, can be helpful. Does somebody want to say what the size of this is?
Also two.
What's the worst case?
That's n times the edge probability.
Yes, yeah, which if it was kind of probability 1.
Edge probability is 1, so it's n.
Yeah, so it'd be n squared.
Can you explain that?
Sorry, it's n for the number of, so I'm going to change this real quick. We're going to use vertices and edges.
So the vertex is the same as a node, and the edge is the connection? Is that what you're saying?
Correct. So this is a vertex, this is an edge. So this is V times the average number of connections, of edges. This is space forever. There's the cost. So, I think, what else? How are people feeling? We can go cover priority queues if you want, but we can also skip them. I'm going to say we skip them for today. Priority queues are cool. Priority heaps is another name for them. They're very similar in many ways to binary search trees, except for they're optimized for pulling things out. And so you can always find the smallest item, rather than the middle item, something like it, in a binary, or in a priority keep or priority queue. Look it up on your own. You'll probably never need it in an interview, but it's a cool data structure and it's a good way to build kind of an understanding for these things. And you can also implement it either as a tree or as an array. It's kind of a fun little kind of equivalence between them. And at the end, we're going to say, think about the data structures we've gone through. It's good practice to implement them, except for and you can even get kind of a simple implementation of a hash map, but I would say don't bother with the complex one, although you can, it's kind of fun. Try them out, and then think about how hard is it to add something to these, what's like the best cost, the worst cost, what's it like adding something in the middle, at the beginning, at the end. Also, what is the cost of removing something? That's one thing we didn't talk about, but in a binary search tree, it's kind of hard to remove something. And when you do, you have to kind of reorganize other nodes in the list. And so thinking about those costs is worth doing. Next week, we'll talk more about what's the cost of finding an item, which gets into searching. And then, particularly for some of these data structures, rearranging things can be important. So thinking about that process of doing that rotation for the tree, and how would you rearrange something, what are the steps you have to do. And with that, I'd say if you have questions on those, send me an email and I'll probably direct you to the Wikipedia page, which will give you the actual answer, because Wikipedia does a good job of describing all the complexities for these. And we'll stop there for now. Any questions? Yeah. Unfortunately, you just have to cover a lot of data structures. Next time will be algorithms, which will hopefully go pretty quickly, because they're all kind of similar. So they'll use these data structures. Cool.